Hi guys, today we'll talk about multiplication. Well, it's not just regular multiplication, it's about vector multiplication. Now, vector is a special class of quantities in physics that we use namely for terms like velocities, displacement, right? Even something like force, right? It needs to have a magnitude as well as a direction, and we represent it by an arrow. Alright, so this was a vector, and basically now we'll talk about certain operation. The operation that we'll discuss in this video would be about vector multiplication. Alright, so if we have to multiply vectors, we have to multiply two of their properties, namely the direction and their magnitudes. Now, multiplying magnitudes is simple. Say 2 times 2 equals 4, and there is like no question regarding it because it is true. 2 times 2 is in fact equal to 4. But what about this kind of a question? Northeast times northwest. Well, it is absolutely absurd because direction times a direction, I mean, we really have to define what this would be in order for it to make proper sense. But multiplication does not really work for directions, so it's really not going to make any sense. Therefore, instead of normal mathematical multiplications, physicists have defined two types of vector multiplications. They are namely scalar and vector multiplication. Scalar multiplication is also known as the dot product, and this is also known as the cross product. Now, the dot product is represented by this, and a cross product is represented by this. Because of the cross, we have a cross, and because of the dot, we have a dot. Now, it's important that these are the only two types of multiplications that can exist for vectors. Why? Because this kind of multiplication, these two, do not depend on the absolute orientation of the two vectors with respect to the chosen axis, that is x, y, and z. It only depends on the mutual orientation of these two vectors, that is, at what angle or in what direction is A located with respect to B, or B located with respect to A. So it only depends on mutual orientation of vectors, which in this case would be A and B. So that is why only two kinds of products could be defined, scalar and vector. Alright, another way to check is, which is quite difficult for me too, I'll still state it, is that if we rotate these axes x, y, and z, say by an angle theta, and then we evaluate the dot and the cross product, you will see that the actual value of the dot and the cross product would not have changed. However, if we define any other operation under the heading of multiplication of vectors, which is different from dot and cross product, however, it does change when we change our axes and not change the mutual orientation of A with respect to B or B with respect to A, then that will not be a proper operation, because then we would have to worry about the absolute orientation of A and B with respect to Y, Z, and X. Obviously, there is no absolute orientation of any kind of axis that exists in nature. I mean, it's all relative. That is why this is a very important criteria for checking the validity of any kind of operation that we define on vectors. It should only and only depend on the mutual orientation of vectors, not only absolute orientation of vectors. Alright, so let's define the dot product further. A dot product is actually represented as this and is equal to this. That is, A dot B is equal to the magnitude of A multiplied by the magnitude of B multiplied by the cosine of the angle that exists between A and B. And this is because this cosine of the mutual angle that exists between A and B exists, and we consider that in the dot product, therefore it only depends on the mutual orientation. So I'll state it again, this is all about mutual orientation, not about absolute orientation, and that is why it exists, and that is why physicists do consider products like dot and cross. Alright. Similarly, A cross B is equal to A multiplied by the magnitude of B multiplied by the sine of the angle that exists between them multiplied by another unit vector which is given by the right hand rule. Now, for example, if we have a plane to ourselves where A lies here and B lies here, and the angle between them is theta. Now, if someone asks me to find which direction would A cross B vector point, now I actually give the answer by using this rule. I place my four fingers along A and then I curl them towards B. So A is here, B goes there, and my thumb points upward towards the camera. So it's actually jumping out of the plane in this manner. So this would be my direction of n cap. It is perpendicular to A, perpendicular to B, and this is the direction of n cap. So this is also parallel to the direction of A cross B. So another very important property that we just noticed is that a dot product gives us a scalar, whereas the cross product gives us a vector. And on this basis we also define the names, as the dot product is also known as the scalar product and the cross also known as the vector product. Now, usually when we have orthogonal coordinates we represent a vector like this: axi cap plus ayj cap plus azk cap. Similarly, B can also be represented as bxi cap plus byj cap plus bz or zk cap. And from this, A dot B could be written as axi cap plus ayj cap plus azk cap dot bxi cap plus byj cap plus bzk cap. And when we distribute when we use the distributive property over the dot product, we actually get ax times I cap dot bxi cap plus byj cap plus bzk cap plus ayj cap dot bxi cap plus byj cap plus bzk cap plus azk cap dot bxi cap plus byj cap plus bzk cap. Now we have to individually take the dot products of axi cap with bxi cap, bxj cap and bxk cap. Alright, now before we move on, I need to restate this, that vector 1 dot vector 2 is equal to the modulus of vector 1 multiplied by the modulus of vector 2 multiplied by the cosine of the angle that exists between them. So when we have our x, y and z axis such that this is x, this is y and this is z, and I cap is oriented along x, j along y and k cap along z, so I dot j must be equal to magnitude of I, that is 1, multiplied by the magnitude of j, which is 1 again, multiplied by the cosine of the angle that exists between them. Now the cosine of this angle is cosine of 90, and cosine of 90 is actually 0. Hence I dot j is in fact 0. Similarly, j dot k is 0, and k dot I is again 0. So if I take the dot product of this with any other of these two vectors, I get a 0, or this with any of these two, 0, or j with any of these two, I get a 0. So using this property, I can expand this and say, what would this be? Well, I would say it is ax, then bx, and I dot I. Well, I dot I would be equal to 1 multiplied by 1 multiplied by cosine of 0 degree, which is equal to 1. So I can therefore write a dot b would then be equal to ax bx plus ay by plus az bz. And this is a very important result that we get from this, from representing a and b vectors as this. Similarly, we get a similar result for the cross product. A cross b would be equal to ax I cap plus ay j cap plus az k cap multiplied by bxi cap plus byj cap plus bzk cap. Now, in order to expand this and get the value of a cross b, we use the determinant rule. The determinant rule is that we actually write this cross product equal to the determinant I, j, k, and then we write ax, ay, az, and then we write bx, by, bz. Remember, the first one goes on the top, the second one goes on the bottom. I mean, when we only compare these two, obviously I, j, k will obviously go on the top of the determinant, whereas amongst these two, a will go on the top and b will go on the bottom. Alright, so this can be expanded as I, this, then we take bz, ay minus az, by minus j cap, which could then be written as bzax minus az bx. Then we can write this as plus k cap, and then this would be equal to ax by minus bx ay. And this is actually a cross product. Now it's a really lengthy formula, so we really do not use it as it is. We actually write it in the determinant form, and then we evaluate when we have a, b, ax, bx, by, and all of these individual coefficients. Anyways, this is how we represent the cross product, when we can represent a and b as a combination of orthogonal vectors that is in this form. Alright, thank you.